On the lab from yesterday, so let's kind of lay out the big picture. So there we've got inclined planes. That's the last big topic, and then we'll have a lab on that on Monday, and then we'll review on Tuesday, and the test over forces will be Wednesday. And then we'll see where we're at in terms of, I doubt we're gonna have a midterm, because that forces test is gonna cover about everything that you're gonna do, because you have to do acceleration and that type of thing. So, what we'll probably do is just jump right into, the next unit on projectile motion on that Thursday and Friday. So, that last big test will then be on Wednesday. Now on Monday, I will not be here at the beginning of the class, shocking, but I've got to go to the funeral of an old family friend, who's actually my sponsor when I got confirmed, so known him for years, so I got to go to that funeral. I'll probably be back by about 12:30, because the funeral starts at 11, it's just down at Schulte, so as soon as the funeral gets back, I'll get back up here. So I should be back about 12:30, so what's going to happen is that I'll have a video that will explain the lab, and so the sub's just going to have you guys watch that, and then you'll get started on the lab, and I'll be back, and then we'll go from there. So that's kind of the plan on Monday. Okay, so let's chit chat about the lab. So oddly enough, this was brought to you by the idea that force net equals force applied plus force opposing. So here's the main idea. So when you all started this, you took that cart, you had a mass that was suspended by the end of it, okay? And then you said, okay, what's going to happen? So if something's going to accelerate, you obviously have to have a force because of Newton's first law. Newton's first law says, hey, you don't apply a force, you're not going to accelerate. Okay, so then it's okay, what can we use to apply a force? So one option is that we could just push it, okay? But the problem is that we're pretty good at a lot of things, but applying a constant force isn't one of them. So it's what do we have available? Gravity, that's kind of a cool thing. So basically what we're going to do is we're going to let gravity apply a fixed amount of force to that system. And so you initially had a 10-gram mass, and you changed that into kilograms, and you multiplied that by G, and you got 0.098 newtons, okay? So that's the force available to accelerate the system. So that's going to be your applied force. That's what's going to make this thing move. So what we assumed was that there was no opposing force. We assumed that the track was frictionless. There wasn't an incline, so we didn't have to pay the frictional mafia. We didn't have to pay the gravity mafia. Nothing. Now, was gravity pulling down on the cart when it's up there on the track? Yeah, it was. But the track was providing a normal force to balance that out. Okay? So this is why this up there is not an opposing force. Okay? Does it have inertia? Yes. Does it resist a change in velocity? Yes. And how we take that into account is when we take that 0.098 newtons and we divide it by the total mass of the system. So let me emphasize this again. When you're calculating a theoretical acceleration, you always divide by the total mass of the system. Just not what's on the end, just not what's up there on the cart, because that whole thing has mass, that whole thing has inertia, that whole thing resists a change in your velocity, okay? So your last step, no matter what the arrangement is, you always divide by the total mass of the system, okay? So what you should see is that your acceleration with the 20-gram mass is twice as big as your acceleration on the 10-gram mass, because you're applying twice the force to the same mass, you should get twice the acceleration, okay? Got that? So Then you got some questions to answer over there on that second page, okay? Now here's what I want you to look at. And this is my whole thought process on how I wrote these questions. I said, okay, here's this little 10-gram mass, and then you have the 20-gram mass, okay? And in this situation, I'm saying, we're just gonna drop these, okay? There's no strings attached, we're not dragging the cart, we're just gonna cut this, we're just gonna cut it. So what I want you to see is that the force that acts on the 10-gram mass is half the force that acts on the 20-gram mass, okay? So this is, when you cut it, you got 0.098 newtons on the 10-gram mass, and you got 0.196 Newton force acting on the 20-gram mass, okay? So there's twice the force acting on twice the mass when gravity is the only thing in town, okay? So the misconception, and this is what I was trying to get you to think through on those questions on number 9. It says, oh, gravity is the same for everything. No, gravity is not the same for everything, okay? There's twice the force on twice the mass. So the amount of force is proportional to the amount of mass. So don't tell me, oh, gravity is the same for everything. It's not, okay? That gravitational force is proportional to the mass. Now, do you end up with the same acceleration? Yes, but don't confuse force with acceleration. The only reason that you end up with the same acceleration is because that force is proportional to the mass, but that mass is proportional to inertia. So the more mass that you have, the harder it is to get it to move. But once you get it moving, it's harder to get it to stop. So that's why when you drop two different masses, you end up with the same acceleration. Not because the force is the same, but because the force is proportional to the mass, so you end up with the same acceleration. So that's what I was trying to get you to think through, okay? So like on that first one, it says everything is in a state of free fall, accelerates at the same rate because the force of 9.8 meters per second squared acts on it. First off, what's force measured in? Newtons, okay? 9.8 meters per second squared isn't even a force, okay? It's an acceleration, okay? And the whole point of 9a is that if you go back up and look at questions 6 and, on those calculations on 4 and 6, you'll see that it isn't the same amount of force, okay? And the force isn't 0.0, even if it was a force, that's still not it, okay? Just go back and look at those calculations. Oh, yeah, it's not 9.8 as a force, okay? You use 9.8 as an acceleration to calculate the force, but that isn't the force. Okay, cool with that page. Now, here's what changes on page 3. So now we're going to take a little block of wood, and we're going to use this as a transition into inclined planes, which is what we're going to talk about today. So now we took that same 20-gram mass from the end of the string, and now we're going to put it on a little bit of an incline, okay? So Topher, what did you notice about the time that it took once you put that block of wood underneath the front edge of that ramp? Okay? So what did that do to your acceleration? Make it bigger or smaller? Smaller. So there's an inverse relationship between time and acceleration, okay? That took longer, so the acceleration was less, okay? So what you want to think through is what you're holding constant and what you were changing, okay? That's the whole key to this. What do you hold constant, what are you changing? So if you look at that 20-gram mass, is it still the same applied force? Yes, because it's the same mass, okay? So your applied force is staying the same, okay? Now, what's happening is that now you got to pay a little bit of money to the gravity mafia. So you still have the exact same applied force, but now you got to take some of that force and give that to the gravity mafia. So what's that going to do to your net force?
Decrease.
Make it smaller, okay? With the smaller net force, therefore your acceleration is going to become
Smaller.
smaller, okay? That's the thought process that I want you to go through, okay? Now, as it goes steeper and steeper and steeper, what's going to happen to the amount of money you have to pay the gravity mafia? It increases, okay? Because as it goes steeper and steeper and steeper, you got more and more money to the gravity module. Cool with that page. Okay. Now, Diane asked about the last page, okay? So, here's the setup. Now, I purposely, very purposely chose the masses that I did for this last page, okay? So on this one, you got a 200-gram mass suspended over the end, and you got a 240-gram mass up there, okay? So notice that I chose the same masses that you used on an Atwood machine, okay? So on the day before, you had 200 and 200, 240 and 200, right? Now, if it was the Atwood machine, here's your 240, and there's your 200. So let's talk about the difference, okay? So if it's suspended over a pulley, and I've got a 240-gram mass over here and a 200-gram mass there, which direction is the system going to move? Down towards the 200 or down towards the 240? Down towards the 240. So in this situation, the 240 is going to drag the 200 up. Okay? Everybody cool with that? So we're going to call this the applied force. We're going to call that the opposing force. Okay? That's what's going to happen. Now, I have the exact same masses, and I put them on a table. Okay? Still got 240, still got 200. The exact same masses are involved, right? But here's the question. Why doesn't the 240 drag the 200 up like it did over there? What's the difference? Still the same mass. Gravity is still pulling down on 240 just like it did over there. No, this is just flat. John.
Yeah.
What'd you say?
Is the force normal acting up because since the table's below it, yeah.
Beautiful. Okay? So on this one, the table is balancing that out. Gravity is still pulling it down, okay, 2.16 newtons, but the table is providing an upward force to balance that out. Whereas over there is no normal force. So that's why that one falls in the direction of the 240. So this one, the 200 drags the 240. This one, the 240 drags the 200. Okay? That's why I chose those specific masses so we could compare those two. So, what you're going to look at on number 10, let's say you get to number 10 and you go, I have no idea how to work this problem. Okay? Go back and look at what you did on the front page. Okay? How did you get the net force? Oh, you took the mass that was suspended from the end of the string, you multiplied that by the acceleration due to gravity, and then what did you do as your last step? To get your acceleration, what do you divide by? Total mass. So your answer to number 10 should be between 4 and 5 meters per second squared. Okay? Somewhere in that ballpark. Now, what I'm looking for on number 11 is an equation. So what should happen is that you should be able to take your answer to number 11 and give it to the person beside you and go, hey, could you take what I have written down on number 11, assuming that you don't know how to do these problems, and could you read my answer to number 11 and know how to find the solution? Okay? That's kind of your litmus test. Now, I tell you, identify all the variables. Okay? You're going to have two different masses. You're going to have the mass on the table, and you're going to have the mass on the end of the string. You could call it M string, M table. You could call it M1, M2. You could call it M hanging, M table. I don't care, okay? Just make sure that I know what it is, all right? Just don't say, oh, it's M times G. I don't know which mass you're talking about. You talking about the one on the end of the string? Are you talking about the mass on the table? Are you talking about the combined mass? I don't know. Yes?
I was just gonna ask if it was alright if we just wrote it out.
Yeah, that's fine. Okay?
Cool.
So literally, if you're not sure if what you have down on number 11 makes any sense, give it to someone else and go, hey, can you think through the thought process that I have? Okay? And if they can, you'll probably be okay. And if they look at that and go, I have no idea what you're doing, that's bad. Now, when you get 12, 13, and 14, here's what's going to change on these problems. Now there's going to be friction. So listen to me, 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 listen to me. When you calculate a frictional force on a situation like this, and I promise you there's going to be one like this on the test, you mark my words, it is going to be the last problem on the test. I'll even tell you which problem it's going to be. It's going to be the last problem on the test, okay? And you're going to have a situation just like this. You're going to calculate an acceleration without friction, and then you're going to calculate an acceleration with friction. It's going to be the last problem on the test. Mark my words. So, here's the deal. When you calculate that frictional force, only use the mass that's on the table. This mass that's hanging down, that has nothing to do with it, okay? This will not contribute to the frictional force because it's not in contact with the table, okay? This thing couldn't generate a frictional force with the table if it tried because it's not in contact with it, okay? So when you calculate the frictional force, only use the mass that's on the table, okay? Only use that. You could bombard the elephant and hang it from the end of this string. It's not going to change the frictional force that exists up there, okay? So to calculate the force to pay off the gravity mafia, you're just going to use mu mg, okay? I've given you the coefficient of friction. Take the mass that's up there on the table, multiply that by g. Get a number. Then decide, am I going to make that positive or negative? So your frictional force on number 11, okay? On number 12, okay? On that frictional force, that should be a pretty small number, okay? Very much less than 1. So then, what you're going to do on 13, you're going to go, same thing. Set up a chart and go, I got some force applied, I got some force opposing, I've got a force net. So your force applied is still the same because you still have the same weight hanging from the end of the string. So whether there's friction or not, it doesn't change the applied force because it's still the same weight hanging from the end of the string. Then you're going to have some opposing force, which is what you have to pay to the frictional mafia, okay? And then you're going to have a net force. Now to get your acceleration, you still divide by the total mass of the system. So now, hopefully this makes sense. Your acceleration on number 10 is about 4.5 meters per second squared, okay? Why should your acceleration on 13 be less than that? Bingo, okay? You got to pay off the frictional mafia, okay? So your acceleration on 13 should be around 4, okay? So you're going to drop from about 4.5 down to about 4 because you've got to pay off the frictional mafia. Now, when you get to number 15, okay, now we're going back to the old school with the Atwood machine, which is the single pulley. So on 15, you're going to use the 240 and the 200. And again, on this one, here's what's different. On this one, and this is why I chose I chose to use the same masses in both situations. So on 15, the 240 becomes the applied force, and the 200 becomes the opposing force, okay? And that's the difference. So your acceleration on number 17, okay, if you do all of that right, that acceleration should be a little bit less than 1 meter per second squared, okay? Are we good, Dime? Okay, yes, ma'am.
So on 18, did you want us to explain that because of so I said it was because they were accelerating in the same direction as the mass, there's no opposing force, but okay, maybe that's not right. Anyways, is it because of force normal, right? Okay, so I should change my answer.
Yeah. Yeah, your answer to number 18 should involve the word force normal. And if it doesn't, just don't write those words on the end. Oh, just write force normal on the end. That'll count. No. 2 days in a row without matching. I can't handle it. I mean, really. Okay. All right. Are we good? Going once?
Wait,
Oh,
on 10 is the answer negative or not?
it's, I just keep it positive. If you made it negative, that's fine.
Okay.
But just, I don't make it negative unless I have to. I'm more of an upbeat, positive kind of guy, though. Now, did you choose your shirt to match the water bottle?
No.
Oh my god, they match really well.
They really do. I mean, I'm
Yeah,
looking
wait,
at
look
that
at
going, wow, it's just kind of, oh dear Lord, okay, that's a good match. Okay. All right. Are we good? Going once, going twice?
Yes.
So stop the on camera.
You look like them. I can tell your siblings.
Okay, so here's our last big topic, and it's inclined planes. So this is one of the situations where we're basically kind of just take everything you already know and just kind of repackage it a little bit. So let's start with something simple. So I take yonder lock, okay, and I put this on here, right? Okay, and I can move this. Now, why doesn't the cart move? Inertia, right? It wants to remain at rest. So
You
I'm moving the
incentive
board underneath it, but the cart itself is pretty much remaining stationary. But I flip it over, that's not near as cool. Okay, so what's the difference? Did I decrease the inertia of the cart?
No, yeah, friction.
What changed? Friction. Okay? So this is a situation where just because you apply a force doesn't mean that you get an acceleration. Okay? So I'm going to take this block, and if it's flat, nothing happens. But if I even put any kind of slant to it at all, I get an acceleration. And if I go steeper, what's going to happen to the acceleration?
Increases.
An increase. So we can sit here and we can draw a fairly simple graph. We can say, okay, we're going to put the angle here, and we're going to put acceleration on the y-axis, okay? So at 0, 0, we'll go to an extreme of 90 degrees, okay? So here's the deal. So if my angle is completely flat, what's the acceleration? 0. Is it because there's no forces acting on the system?
No.
No, there's forces acting on the system, which are gravity and the normal force, but everything adds up to
0.
and we have no acceleration. Now, if I lift this up a little bit, I get an acceleration. Now, is there a chance, when I let go of this, that at any point, this cart is going to start accelerating up the hill? No, that would be really, really weird. Okay? It's like, what's the lab that you did in physics today? We lifted up a board and we let go of it to see if it would ever go up the hill. Okay? Well, that was productive. Okay? No, you'd be like, okay, this is the dumbest lab we've ever done. And it would be. That's why I don't have you do that. Because so every time, the gravity mafia is going to make you go which way? Up the hill, down the hill. Down the hill, okay? You don't have to worry about getting off the ski lift on the mountains in Colorado, and all of a sudden gravity starts making you go up the hill, okay? It's not going to happen, right? You know it's going to act down the hill. So, what's this graph going to look like? This?
Yes, it's a direct relationship.
Okay? So as the angle gets steeper, the acceleration's going to get
Bigger.
bigger.
Maybe it stops at negative 9.8 though.
And I don't get hung up on, well, okay, so here's the deal.
You know?
Let's say I go exactly to 90 degrees,
Oh, God.
and I let go of it.
Yeah.
If I go to exactly 90 degrees, what's the acceleration going to be?
Negative 9.8.
Yeah, just call it 9.8, right? So here's my point. On an inclined plane, my maximum acceleration is going to be 9.8 meters per second squared. So if you ever calculate acceleration on an inclined plane and you get something bigger than 9.8 meters per second squared, you have done something horribly wrong. Okay? Cool with that. Now, if F equals ma, and it does, what has to happen to the force, the value of the force, to create a bigger acceleration? It has to increase, right? So to create a bigger force, that's going to require a bigger acceleration. Okay? I ought to teach you the faith on that one. Okay? So when you talk about forces on inclined planes, there will always be 3 of them. Okay? So when you have any inclined plane problem, no matter what, so I'm just going to draw this box, and I'm going to let the mass be 1.02 kilograms. Okay? So, and I'm going to let this be a 30-degree angle. Okay? So, here's the 3 forces that always happen. And there's 2 different ways that you can draw this. It's a personal preference as far as how you draw this. Some people like the different methods. Which one you pick makes me no difference. Okay? But no matter what, you're always going to have gravity acting straight down. And that's still going to be mg. Now, do not, Marilla, listen to me. Do not make this a negative value. All you're using this is like a gateway force to find the other, everything else. So do not make this negative. Just get the number, okay? Just get the number. So if you take 1.02 times 9.8 meters per second squared, trust me, you get 10.0 newtons. That's my FG. So gravity is always going to be acting straight down. So when you draw these vectors, your gravitational force always acts straight down. There's no angles to it, boom, straight down. Okay? Easy peasy. Now, obviously, there has to be a force that's acting down the inclined plane. Okay? Because if there wasn't, then it wouldn't accelerate. So I know there's a force that's going to act down the inclined plane. That, oddly enough, acts parallel to the inclined plane. So, not very clever, but we're going to call that force parallel. Okay? So, there's 2 ways you can draw your force parallel. One is that you can draw it parallel with the plank, and it's always going to point down the hill. That's one way you can draw it. The other way is that you can come over here and draw it as part of a triangle over there. I don't care which way you draw it, it's up to you. Now the third one that's going to be that I'm going to go ahead and draw that out right now, and that's going to be the normal force. Okay? And you can also, based upon a personal preference, you could also draw it like this. Okay? So here's your 2 ways that you can draw these vectors. One is you make it in here like a triangle, and this is going to be a right angle because my force parallel, oddly enough, is parallel with the surface, and my normal force is at a right angle to the surface. Okay? So that makes this a right angle here. Now, this is where the magic of geometry helps out. And no, I'm not going to make you do this proof. Okay? Do they still make you do proofs in geometry?
Yeah, but good
Okay.
thing I had it during COVID.
But what?
Good thing I had it during COVID. Didn't have to do
You
it.
didn't have, really?
Yeah.
I liked proofs.
Okay.
We did it, but
It
like,
was kinda fun.
we didn't really do it. Remember that, Catherine?
I had Mrs. Provencher though.
Yeah, we
You
did
had, you had
Miss Fair
geometry
together.
COVID, huh?
During COVID. Yeah, COVID geometry.
Okay.
That's why I always get it wrong on the
As opposed to non-COVID.
Yep.
Okay. All right. Now, here's the deal. Whatever angle the inclined plane is whatever the angle of this triangle is going to be. Okay? And if you go through like alternate material angles and do all the proofs, you can prove this. So the beauty of it is, it isn't like, you don't have to subtract it from 90, it isn't like a complementary angle, anything wonky like this. So whatever angle this is whatever angle that is. Okay? There's nothing to think about. That's going to be the same angle. So this is where depending upon your preference, how you want to draw this. So if you go off this angle up here, the weight of the object, which you were always going to know, that's the one value you will always know, is the weight of the object. That's going to be the hypotenuse. So then these are either going to be the side adjacent or the side opposite. So this is why it just works out to be a trig function problem. So Maggie, I know the hypotenuse is 10 newtons in this case. This is a 30-degree angle. What trig function is going to allow me to find the side opposite that angle?
Sine.
Sine. Okay? Fantastic.
So good to learn.
So the sine of theta is going to equal that side opposite, which is what I'm going to call force parallel, over FG. So Maggie, how am I going to get force parallel by itself?
Multiply FG on both sides.
Fantastic. So on your equation sheet, you will see this. Force parallel equals FG sine theta. Okay? This is where it comes from, is that geometry. Okay? Now, Maggie, since we're on a roll with trig functions, force normal is the side adjacent. So what am I going to use for that one?
Cosine.
Cosine. So the cosine of theta is going to equal force parallel, force normal, over FG. So force normal is going to equal FG cosine theta. Now, when if you hearken back to when we first started forces, okay, and we were doing that very first lab when you were going to pull something at a constant velocity, and I said, this is technically how you calculate force normal, is FG cosine theta. But up to this point, what has the angle always been? Zero. Cosine of 0 is 1. We never had to worry about it, okay? Because it was just 1. But now that we're on inclined planes, now we have to worry about that angle, okay? Now we have to worry about this. So, I'm going to redraw this and kind of clean this up a little bit. So, I've got my FG, which is 10 newtons. I'm going to draw my force parallel out here. I'm going to put my force normal here. Now, if you like triangles, it's like, oh, Mr. Burkamp, I was the president of the triangle club. Let's draw it as a triangle. Cool, okay? So if you want to draw it as a triangle and put your force normal here and your force parallel there, that's cool, okay? How you draw it makes me no difference. Just pick the system that works best for you, okay? Just pick one. All right, so here's the drill. Let's calculate that force parallel. So my force parallel is going to be FG sine theta. So in this case, that's going to be 10 newtons times the sine of 30 degrees, which should get you 5 newtons. Now, at this point, we need to make a decision, okay? We need to make a decision. Do you want downhill to be a positive or a negative value? Okay, because that's the decision that we have to make, okay? So, how do you want to play out? Negative? You sure? Okay, fantastic. So, in this system, we're going to make, and this is, we'll stick with this. So from here on out.
Forever?
No.
Oh.
Now, I'm going to work downhill as being a negative value. You don't have to. If you go like, oh, Mr. Burkamp, I want downhill to be positive. You can make downhill positive. There's no right or wrong answers. I don't care. It makes me absolutely no difference how you define your system. Okay? Makes me no difference. Pick one. Now, there are going to be certain problems where I will tell you, hey, this is how I want the system defined. Okay? But unless I specifically tell you how to define the system, it's on you. Okay? If you want downhill to be negative, fine, we'll make downhill negative. If you want downhill to be positive, we can do it positive. It doesn't make any difference. But you do need to find a system and stick with it. Okay. So, I've got my force parallel as -5 newtons. Now we need to find that force normal, which is, so somebody take 10 times the cosine of 30. It's 8 something. 8 point what? 8.66 newtons. Okay? So this is going to be 8.66 newtons. Okay? It's cool. All right. Now, there's a couple of ways that you can show how this changes. One option is that you go through the math. Okay? So if you go through the extreme case of the math, and this is where this whole system works. If you go back to a flat surface, okay, if you go back to a flat surface, what's the force parallel going to be on a flat surface? What's the sine of 0?
0.
0. Sine of 0 is 0. So
With
this
the
is
sine?
why if you're on a flat surface, guess
See
what?
what? Sine of 0 would be 1, I thought.
That's
No,
cosine.
it's 0.
Of zero?
Goes
Zero is
cosine
parallel.
sine. No, it doesn't. Oh, yeah, it does. Yeah.
Oh, yeah. I had to think about my unit circle there.
You're confusing
Because I was like,
me.
oh, wait, you just go straight up. But that's 90. Never
Yeah,
mind.
yay for the unit circle.
Yep.
Ugh.
Okay? So, on a flat surface, if you take the sine of 0, you get
0.
multiply that by the 4 10 newtons, check my math, you're going to get 0. So this is why on a flat surface, there is no force parallel. But on a flat surface, the force normal is going to be 10 newtons in this case. Because if you take the cosine of 0, you get 1. 1 times 10, check my math, gets me 10. Now, let's go to the extreme. Let's go vertical. Okay? Now, when we go vertical, what's the cosine, or what's the sine of 90?
1.
1. Now, if I go to the extreme and I go to a 90-degree angle, my force parallel is going to be, in this case, 10 newtons. Because now all of the force is acting down the hill. But what's the cosine of 90 degrees?
0.
0.
No force
So
normal.
when I go to 90 degrees, guess what? There's no force acting into the board.
Wow, that
Okay.
is cool. How many forces are there?
How many what?
Like, how many forces do we have to learn?
This is like the last one.
So this is all the forces?
Oh, well, we'll still have like centripetal force to go. And gravitational force in different calculations.
Okay.
But we're about there.
Okay.
Okay. Now, so one of the things that you can do is I've got this handy dandy little device here, just for this occasion. So what this is that it's got a little like digital scale, okay? And come on,
Oh my gosh.
I'm gonna hook this up.
So that's high tech.
Hold on.
Oh my god, it's quite.
There we go. So it's sitting here, oddly enough, reading 0. And I hooked a little cart, and it's got a little weight on the inside of it. And the the scale is reading 85.6 newtons. So here's what I want you, so we're sitting flat, and the scale is reading 85.6 newtons. Now, I've also got a spring Newton scale here, okay? And that scale is measuring how much force is being pulled parallel with it. So I'm on a flat surface. Notice that this has no reading at all, 0. The scale is reading 85.6. So the scale is balancing out the pull of gravity at this point. So what I'm going to do is I'm going to lift this up, okay? So as I lift this up, what do you think is going to happen to the reading on that digital scale that's sitting down here and that weight is sitting on top of it?
Decrease.
Increase, decrease, or stay the same?
Decrease.
Decrease, why?
Because the force normal is becoming less.
Okay? But what should happen to the reading on this scale?
Increase.
Should increase. So as I lift this up, let's go up to like, in this case, about 20 degrees. So I went to 20 degrees. This scale here, which is that spring scale, is up to about 0.26 newtons, okay? So I've lifted it up to 20 degrees. This went from 0 to 0.26, but the reading on this scale went from 86 down to 75, okay? So it's exactly like we predicted. So the scale, basically, what we're doing is we're taking that gravitational force and we're breaking it up into two components. So because of the fact that this table doesn't have to balance out as much as of that gravitational force, which is acting straight down, so at this point, some of that force is only being directed like this. We've taken some of that force and put it into that force parallel. So as I go, raise this up a little bit, just more on the scale. So then, if I go up to, say, 45 degrees, okay, now this has gone up to about 0.75 newtons. The reading on the scale has dropped to 48.2. So as I'm going higher and higher and higher, don't think, oh, gravity is getting weaker and weaker and weaker. No, gravity is still acting straight down, but the table is providing, has to balance out less and less and less of that force because of the fact that it's acting more and more down the hill. Got the idea? Now, if I go all the way to, we can go all the way up to like 70 degrees, okay? We go to 70. This is all the way up to about 1 Newton. The reading on the scale is like 1.2, okay? So if I go all the way to 90, what's going to be the reading on the scale? 0, because all that weight then is going to be acting down the hill. Got it?
Yes.
Fantastic. Okay. Yeah. Now we need to look at how do we use all this. Okay. So we're going to look at some different scenarios. Scenario number 1, still the same 30-degree angle. And we're going to assume initially that this is a frictionless surface. Okay? This is the magic frictionless surface. Okay? So I'm going to lift this thing up to 30 degrees. Same mass, so we don't have to redo any calculations. Okay? Gravity is still pulling down at 10 newtons. My force parallel, you still want to stick with downhill being negative? Okay? So my force parallel is negative 5 newtons. And I've got my force normal. So imagine this. I'm going to set this thing at a 30-degree angle like this. That's about 30 degrees. I'm going to hold it here, and I'm just going to let go of it. So what I want to know is what's the acceleration of the cart. Now, we're going to do the exact same thing that we've done before. We're going to set up a chart. We can have force applied. We can have the frictional mafia. But now, we're going to have the parallel mafia, which is a subset of the gravity mafia. And then we're going to have our net force. Okay? So, of these three, as you're on an inclined plane, the only one that will never, ever be 0 is your force parallel. Okay? You can have no force applied. It might be a frictionless surface, but you will always, always, always have a force parallel. Okay? No exceptions whatsoever. So what I set up here like this is a 30-degree angle, and I let go of it. I have no applied force. That's 0. It's a frictionless surface. There's no frictional mafia. That's 0. What's my force parallel? Oh, negative 5 newtons. So my net force is just negative 5 newtons. So if you were to draw this out, this is what this diagram would look like. You would have these three: your gravitational force, your force parallel, and your normal force. So when I ask you to draw vector diagrams of force parallel, and I am on your assignment and in the lab on Monday, okay, when I ask you to draw the vector diagrams for inclined planes, at a minimum, there is 3. Gravity, normal, force parallel. You always have those 3. No exceptions whatsoever. You always have those 3. Okay, so my net force is -5 newtons. It's the only game in town. That's it. There's nothing else, right? There's no squirrels, there's no friction, nothing. So how can I find my acceleration?
F net divided by mass.
Yeah, so I can take my net force, which is -5 newtons, and divide that by 1.02 kilograms, and you're going to get -4.9 meters per second squared. Okay? So that's about half the gravitational acceleration. Everybody tends to think, oh, 45 degrees is when it should be like half, because 45 degrees is like half of 90. Oh, at 90 we're at -9, or no, we're at 9.8, so at 45 we should be at 4.9. No, it actually occurs at 30 degrees. Now, here's the other way that you can do this. If there's no friction, and this only works if there is no friction, your force net divided by mass gets your acceleration. So this is a little trick of algebra that you can do. Well, if it's on a frictionless surface, your net force is the same as your force parallel divided by mass. Your force parallel is Fg sine theta divided by mass. Well, Fg is mg sine theta divided by mass. Your masses cancel out. Take your gravitational acceleration, multiply it by the sine of the angle. There's your acceleration. Okay, but that only works if there's no friction. Okay, that's the only time it works. So that's why, if you're not sure, go through that process. And you all actually use this. If you remember back to the very first acceleration lab that you all did, where you pushed the cart up the hill, and I said, hey, here's how you're going to get your theoretical acceleration. You're going to use A equals G sine theta to get a theoretical acceleration. That's where that comes from. I said at some point you will see where A equals G sine theta comes from. That's how you get a theoretical acceleration if there is no friction. Okay, cool with that one. Now, here's the next step. If I said, how much force is needed to pull the block up at a constant velocity? So, what are the 2 most important words in this? So what do you want the net force to equal? 0. So in other words, I'm going to set this at 30 degrees, and I want to push this thing up the ramp at a constant velocity. Okay? Just going up like this, right? Push it up at a constant velocity. So, still no friction. So, when in doubt, come back out here and say, okay, I'm going to set up this chart. I got force applied, I got force friction, I got force parallel, I've got force net. What's your net force going to equal? 0. What's the value of your force parallel?
-5.
-5 newtons. There's no friction, so what does my applied force have to equal?
5.
Or 5.
5 newtons. Now, hopefully that makes sense. Oh, that's cool. Because if you think about it, you want to push this thing up the hill. Which direction are you going to push?
The opposite.
Up the hill, right? Okay. So if I want this thing to move up the hill at a constant velocity, I have to apply a force equal and opposite to the force parallel, so that everything adds up to equal to 0. Got the idea? So now, on your diagram, what you would do is you're going to sit here and go, okay, here's my block, here's my FG, there's my force parallel, there's my force applied, there's my force normal. Now, when you're making these add up to equal to 0, only worry about the forces that are in this direction of motion. Don't throw in FG, don't throw in force normal, don't include those. Okay? The only forces you're worrying about are the forces in the direction of motion along that plane. Yes?
Wait, so on our assignment, if like it's asking about this, like a question like this, you only want force parallel and force applied on the diagram?
No. In terms of your calculations, you want to,
Oh.
when I ask you to draw all the vectors,
You do want everything?
oh yes.
Okay.
But in terms of this, some of the forces, only consider the forces that are in the direction of motion. In other words, don't throw in 10 and 8.66, anything like that. Only involve the forces that are in that plane of motion. Okay, second to the last one. Same block, same 30 degrees, same mass. But now I tell you that the coefficient of friction is 0.1. Now there's friction. Okay? So once you know mu, what do you think once I give you mu, what do you think I'm going to expect you to be able to calculate? Force friction. Now, you know that mu times force normal equals force friction. So that's U times Fg cosine theta. Now, up to this point, we didn't have to worry about the cosine part. We could just use O mu mg. That's all we had to do, is mu mg. Now you're on an incline. You have to take the angle into account, okay? You have to use the angle. So in this case, I'm going to take mu, 0.1, times the 1.02 kilograms, times g, times the cosine of 30 degrees. So we know that this whole thing, which we've already calculated, what was it, 8 point something? What was that, 8.66. Or you could just take 0.1 times 8.66 newtons, and that's going to get you 0.866. Okay? Now, which direction, Michael? So here's the situation. I'm going to have it now like this. So now I'm going to like put this wheel side up. So when I let go of it, which direction is my frictional force going to act? Up the hill, down the hill. I'm going to let go of it. It's going to slide downhill. Which direction does friction act? Up or down? Up. So friction on an inclined plane always acts in the opposite direction of motion. Notice I did not say it always acts up the hill or down the hill. I just said it acts in the opposite direction of motion. Okay? So if you were to draw this out, this is where the frictional mafia and the gravitational mafia intersect, is on inclined planes. So I've got my gravitational force, 10 newtons. I've got my force normal. My force parallel is -5 newtons. Now, where am I going to put that frictional force?
Opposite of the parallel.
Yeah, so that's going to go 0.866 newtons up the hill. So, what's going to happen to my acceleration? Is my acceleration going to be bigger or smaller once there's friction? Smaller. So this is why, from a physics perspective, the Winter Olympics should be called like the force parallel games. Okay, no, seriously. Look at downhill skiing, look at bobsled. All those events that involve going down the hill, okay, what do you want to minimize? If you're going to win, what do you want to minimize? Your frictional force. So because that maximizes your acceleration. This is why skiers don't go down the hill with a sheet of plywood strapped to their back. Okay? It's like, oh, that's cool. I'll have no. What do? They go in a very, very small tuck position. Okay? Because they want to minimize that drag. So from a physics perspective, the Winter Games are just the downhill inclined plane games. And then, well, there's curling, but that's conservation of momentum. That's also physics. Okay. And if you ever want to go to sleep, try to watch curling. It is impossible.
Is that the mop one?
Huh?
Is that the mop?
Yes, with the
Why is
broom,
it-
the sweeping. Yeah, it is impossible. It is physically impossible to stay awake and watch curling. It cannot be done. Okay, so here's what we've got. I'm going to ask you to calculate the acceleration. So right away, Riley, When I ask you to calculate the acceleration, what is your net force not going to equal?
0.
0. So, we're going to set up a chart. We're going to go force applied, force parallel, force friction, force net. So force parallel is still negative 5 newtons. I let go of it, so there's no applied force. We're not pushing it, we're not pulling it, nothing like that. That's just going to be 0. What's the value of my frictional force? 0.866. Now, this is where you pay attention to the sign. Is that going to be a positive or negative value? Why?
It's uphill.
It's going up the hill. So I got a negative 5 Newton force going down the hill because of the friction, because of the gravity mafia. The frictional mafia is going up the hill at 0.866. So the difference between those two is going to be my net force. Okay? So that's going to be 0.866. So somebody take negative 5 and add that to 0.866. Negative 4.13 newtons. Now, what's happened to my net force? It's become smaller and negative. Okay?
Yes.
So what's going to happen to my acceleration?
To be smaller.
It's going to become smaller, right? So somebody take negative 4.13 and divide that by 1.02 kilograms. Negative 4.05. So what's happened to my acceleration? It's become smaller. Okay? Cool with that. Here's the last one. And the beauty of it is we don't have to calculate anything new. So I want to know how much force it takes to pull it up at a constant velocity if mu equals 0.1. Okay, so visualize this. Here's the situation. I got an inclined plane. I have friction, but I want to push this thing up at a constant velocity. So, which direction is force parallel going to act? Down. Now, this is the tricky part. Which direction is that frictional force going to act?
Down.
Down. Because it's in the opposite direction of motion. Okay? But what do I want my net force to equal? 0. So think about this. As this thing is being pushed up the hill, right? It's being pushed up the hill. I have to overcome two forces which are acting down the hill. Now, the mafias have joined forces. Okay? It's like, oh, seriously, right? So now the downhill mafia and the frictional mafia are working together. So now to push things up the hill, you have to overcome both mafias. And it's like, oh, seriously, yeah. So here's the deal. So the beauty of it is we don't have to do any new calculations. I've still got my force parallel. That's still negative 5 newtons. I still have my gravitational force. I still have my force normal. My applied force is going to be going up the hill. Now here's the kicker. Which direction is friction going to act? Down the hill. And that force friction was negative 0.866 newtons. So here's the deal. I got a downhill force of force friction. Now, notice here I made this negative. In the previous problem, friction was positive. That's why I said, don't get this wrapped up in your mind, oh, friction is always negative. It depends upon how you define your system and which direction the block is moving. So if that block is moving up the hill, friction is acting down the hill. If the block is sliding down the hill, friction is acting up the hill. Okay? That's why I said be careful about saying, oh, friction is always negative. No, friction is just always in the opposite direction of motion. Okay? That's the kicker. Okay? So what's the value of my applied force going to be?
5.86.
5.866, because you have to overcome the two forces acting down the hill. Okay? So, again, if you're into charts, I highly recommend that. So you got force applied, force parallel, force friction, force net. What do you want that net force to equal?
0.
0. So my force friction was negative 0.866. My force parallel was negative 5, which means my applied force has to be 5.866. Easy peasy, lemon squeezy. Stop that. Let me hand out the assignment.
Devin is
Okay.
going.
So here's the story. You got a 2.8 kilogram box. All I'm asking you to do is calculate this. On number 1 and number 2, do not worry about making any of those negative, okay? Just give me the numbers, okay? Literally, do not worry. All you're doing is, hey, do you understand how to calculate this? Make sure that your calculator is not in radian mode. Make sure that you are in degree mode, okay? Make sure of that, please. Otherwise, you're going to get answers that make no sense whatsoever. Now, when you get to question number 4, you got a 1.2 kilogram box rests on 20-degree hill. In your system, uphill is defined as positive or negative, downhill. I don't care which one you pick. But how you answer number 4 is going to drive how you answer 5, 6, and 7. Okay? So once I don't care how you set up your system, but once you take that system to the dance, you're stuck with that system at the dance. Okay? There's no right or wrong answers. You just have to be consistent. Now, every place I've got an inclined plane, little triangle, that's where I expect you to draw the vectors. Okay? So, and it says, oh, draw a diagram. Okay? So any place there are this, you draw at least 3 on every one of those. Gravity, normal, parallel. Okay? Some of these you're going to have friction. Some of those you're going to have an applied force. Okay? But at a minimum, you're going to have the 3. There's 2 problems on the back. So on number 9, you've got a 1.3 kilogram box. Frictionless, you want to know how much force it takes to pull it up at a constant velocity. Now, on number 10, here's the deal. You got a 1.89 kilogram box and a 34-degree angle hill. You want to pull it up at a constant velocity, but I've given you the coefficient of friction of 0.18. So, again, anywhere you see the little triangles, I want force diagrams, and you will always have a minimum of 3. Riley?
Do you want the vectors to be a certain length? For
No. Oh, these don't have to be drawn to scale.
Okay.
You just have to draw them and label them. Now, be careful. This is what I don't want to see. When you draw that force normal, do not draw that force normal straight up. Okay? That force normal is acting at a right angle to that inclined plane. So when you draw your force normal, you're used to drawing it straight up because you're used to being on flat surfaces. Okay? You're not anymore. So you've got to draw that at a right angle to that surface. So FG is straight down, force normal is going to be at a right angle to that surface. Okay, I'm done.